So now we are going to talk about continuous random variables, and we start by describing what the probability density function means. This one that I've drawn here looks like the normal distribution. That is intentional because the normal distribution is everybody's favorite example of a continuous distribution. But when you're only studying normal distributions, it is common to only look at this kind of picture as sort of like a diagram that represents the probability and not as the graph of a function. But right now we are going to want to look at it as the graph of the function. And notice how in normal distributions, when we draw this picture, we don't often even put a vertical axis anywhere, or the horizontal one for that matter. So it doesn't really look like it's being treated as a function. And the reason for that is that when talking about a random variable distribution, the values of that function, which would be the numbers on the vertical axis, those values don't really matter. They don't really represent the probability of anything about your random variable. The probabilities are actually represented by the areas under this curve. So the main difference now that we move away from always looking at the same function, which is the normal distribution density function, into dealing with more general functions, any function that we want to handle, it becomes more important to actually see it as a function and to point out the kind of obvious fact that the area under the curve that we've just drawn is the integral of that function from 1 to 3 in this example. So yes, it is a prerequisite for this topic to think that you understand the concept of integration. You've already been through that. Today I'm going to try to not integrate by hand any functions that are very complicated, so you don't really have to be the master of integration in order to follow, but you do need to know the concept and be comfortable with the notation. I'm going to stay most of the video in paper 1 type questions, which means that I'm going to be doing everything by hand. But at the end of the video, I'll give you one example with the calculator, which is really going to be the same kind of exercise, but allowing us to use more complicated functions, because then we're not going to have to integrate anything by hand. So before I erase the normal distribution here, let me just point out another fact that the total sum of all the probabilities in any random variable needs to be 100%. So if the probability of being between 1 and 3 is the integral from 1 to 3, then in order to get this 100%, this integration equals to 1, we need to go from all the way in the beginning to all the way in the end. And that is integrating from negative infinity to positive infinity. Now, in the case of the normal distribution, it is actually going from negative infinity to positive infinity because this density function here has a horizontal asymptote at y equals 0 on both sides. So if you cut it off before infinity, even if it's at a big number like 1,000, you are going to be getting a number that is less than 1 because the horizontal asymptote is not reaching the y equals 0. So there's a tiny little bit of probability that your random variable is going to be bigger than 1,000, no matter what it is representing. But for practical purposes, when we look at the style of problems that the continuous random variables are going to give us, it is not very nice to have functions that go all the way from negative infinity to positive infinity. So usually we work with functions that do something interesting in a very small domain, and then outside of that domain, they are just equal to 0. Like this function here, for example, it is still true that the integration from negative infinity to positive infinity is equal to 1, because this needs to be true for any probability density function. But because this function is equal to 0 after x equals 5 and before x equals 0, then this is the same thing as just integrating from 0 to 5, which helps to simplify the calculations. Which is why you will often see piecewise functions in this type of problem. And another thing that happens very often is kind of like what I just did here, where there is some sort of parameter in the definition. There's this a here that is also appearing in the picture. And the first thing that you're supposed to do in that kind of situation is to figure out the value of a. What do you have that you can use in order to figure out the value of a is that the total area needs to be equal to 1. In this case, I wrote x dx instead of f of x dx like I was doing in the other picture, but that's just because my function is the function f of x equals to x, okay? So that's the same thing. And even though it looks like an integral, in this very simple case, we don't actually need an integral to figure out the area because that's the area of a triangle. And this is something that you should be looking out for in questions, especially in paper one questions. Sometimes it's not about integration at all. Sometimes it is about the concept of integration, but you don't actually need to integrate anything to calculate. What I want is a triangle with base A, height A, and area 1. So what is the value of A? And then you think for 5 seconds and realize that A is equal to the square root of 2, right? Because base times height divided by 2 is the area of the triangle. And then you can start asking the probability questions like we were mentioning before. The probability of this random variable being between a half and 1 is this integral, which you also don't have to think of as an integral if you don't want, because it's just one triangle minus another triangle. So the next set of interesting things that they can ask us to do in this kind of question is to calculate all of the measures of central tendency and dispersion. I'm going to start by talking about the mean and the variance because they are the most common, but then we go ahead and talk about the other ones. So remember when we were doing discrete random variables, we also knew how to do all of these kinds of things. In particular, the mean is the expected value of this random variable. So how did we do that? It's supposed to be the weighted average of all the possible values where the weights are the probabilities, right? So we multiply this by this by this, and then we add all of those numbers together, finding an expected value of 3, which is not really surprising because I made a symmetric example with the middle value being 3. So of course the expected value is going to be 3, but that's not going to happen in our example because that's not symmetric. The analogy, though, is that we have to take x, which is the value that the random variable is taking, and we have to multiply this x by the probability of that value happening, and then we have to add over all the possible values. So we're going to take the values of x, and then we're going to multiply them not by their probability, but by their probability density. Because the probability of being equal to a certain value of x, say 1 for example, this probability is 0 in a continuous random variable, right? You only get non-zero probabilities when you ask for the probability of being between something and something, because then it's going to have a little bit of area. But that's okay here because the probability density is kind of filling that role of being the probability by which we multiply the value. Except we also have to sum that over all the possible values of x, which in general are going to be from negative infinity to infinity, but in this case it's from 0 to the square root of 2. So I know that this is a little bit weird, but it is the same exact kind of weirdness as when we first start talking about integration, right? It's the thing about the limit and adding an infinite number of infinitely small rectangles that have sort of like base times height. And the same thing is happening here. The probability of the random variable being equal to 1 is 0. And f of x is not 0, but f of x is not the probability. F of x is the density. The probability of the random variable being equal to x, the thing that we're multiplying x by when we calculate expected value, is not f of x, is f of x times dx, which is 0 because dx is 0. You see, it is the infinitely small base of that rectangle that we are adding when we integrate. And in this example, at least between the points 0 and the square root of 2, my function is x. So I'm going to substitute this f of x here by another x, which makes this the function x squared. And then we integrate it, getting x cubed over 3. Then we use the fundamental theorem of calculus to take this primitive function applied to the square root of 2 minus the same function applied to 0, which makes the final answer 2 root 2 over 3. Now we can estimate a little bit to see in the picture if this makes sense. So it's 2/3 of the square root of 2, right? So 2/3 of the way to the end of this part kind of around here. And yeah, that looks fine as an expected value. The expected value you can think of as if you put your finger here, will the shape on top of it balance on top of your finger? Is that like the center of gravity, or will it fall to either side? It's supposed to balance, so that's the expected value. Yeah, so now that we already know the mean of this random variable, the next thing that I want to do is to calculate the variance. So this is the variance, right? It is also a weighted average of something. So here are the weights, is the density function times dx, just like in the previous calculation for expected value. This here is giving the weights of the weighted averaging that we are doing. And the integration is part of the averaging process. But this time, instead of taking the average of just the value of the variable, which was the x that we had here before, now we are taking the average of the squares of the distances between the value and the mean. Look, let me point something out here. If you expand this square, you can then separate your integral into three integrals, right? The first one is going to be the integral of x squared times f of x dx. And the other two I want to do separately to show you what's going to happen. This was the second part of the integral. So there are some numbers here that I can take away to the outside of the integral as if I am factoring out that number from the sum. And then this integral that remains here is something that I have already calculated before. This is just the integral that I did to find the expected value. And the expected value was that number. So that's the final result for the second integral. And for the third one, again, this number is going to be factored out of the integral. And that integral over there is just 1 because it's the integration of the density through the whole domain of the function. So when you put both of those together, minus 2 of this number squared plus the number squared again, it's just minus the mean squared. So that's what I'm going to do here. I'm going to replace both of these by just minus the mean squared. And when you see it written this way in the formula booklet, because it is, both this one and this one are in the formula booklet, it looks so much like somebody just messed up a special product. So I wanted to show you that so that you know that's not what's going on. This is actually equal to this in this very particular special context. And this one's going to be easier to integrate, of course, because the number doesn't really even have to be integrated, right? It gets out of the integral and the integral becomes the integral of f of x dx again, which is equal to 1 again. So the minus mean squared can just be put outside of the integral. But the integration of x squared times f of x dx, now f of x in this example is x, which makes this x to the power of 3. And when you integrate it, it's x to the power of 4 over 4. Now we have to apply the fundamental theorem of calculus. And there's a lot of things that are going to simplify here, right? That is 4. This is 0. And this is 8 over 9. So 1 minus 8 over 9, the variance of this random variable is 1 over 9. Which is a really convenient number, right? Because when we ask the next question, which is the standard deviation is the square root of the variance. So in this case, we get a very pretty answer, which is 1 over 3 for a standard deviation. Okay, so I said that I was also going to calculate the other measures of central tendency and dispersion. So let's talk about mode first, just because it's very simple. What is the mode? The mode is the value that appears the most often. The mode is the value that has the highest probability of appearing, but not probability in this case, density. So the mode is the number that has the highest value of density. This is kind of a weird example because the mode ends up being at the very edge of the interval of values that are possible. But that's because it was a weird example to begin with, right? Why is this function dropping suddenly from root 2 to 0? This is a toy example just to illustrate the calculations. So I'm okay with it having a strange answer. But the other measure of central tendency that is very interesting to calculate is the median. And what does the median represent? It is the point such that half of the probabilities to the left and half of the probabilities to the right. So we can represent that as an integral. We should be comfortable representing this as an integral. But again, in this example, is not going to be necessary because we're just talking about the area of a triangle. Just keep in mind two things here. I wrote from 0 to m because the domain of my function starts at 0, but usually this would be a negative infinity down here. We do have to start all the way from the beginning. And just be careful that this integration is not of x times f, okay? We're not averaging anything here. We're just straight up adding the probabilities. Yeah, so what's the value of m that makes the green triangle have area half? Base times height divided by 2 is half, so m is 1. So the formulas that we used for calculating the expected value and the variance, they are in the formula booklet, but the fact that the mode is the most frequent value or the value with the highest probability density is not in the formula booklet, and the way to calculate the median is also not in the formula booklet. Now, although it is far less common to find that in exam questions, there is another measure of dispersion as well that we are familiar with and we can try to calculate here, which is the interquartile range, IQR. So Q3 minus Q1. And to calculate Q3 and Q1, we're going to use the same strategy. We're going to look for the point where the integral is not equal to 0.5 like we did for the median. We're going to look for the point that makes it equal to 0.25, and we're also looking for the point that makes it equal to 0.75. In our case, the value of Q1 that makes base times height divided by 2 equals 2/4 is Q1 equals root 2 over 2. And base times height over 2 equals to 3/4 makes Q3 equal to root 6 over 2. So that's the IQR in this example, root 6 minus root 2 over 2. Now I mentioned already that this kind of looks like a weird example because the density drops suddenly from root 2 back to 0. So let's try to make a more natural looking one. For this one, what I really wanted to do was to take a quadratic function facing down with vertex in the point 1, 1, so that it would have a domain from 0 to 2, and then I can say that it's 0 outside of that domain. So that's why my function looks like this. It's a quadratic function where the x-coordinate of the vertex is 1, and the y-coordinate of the vertex is also 1, and it's a parabola facing down with concavity negative. But I'm not really allowed to just choose the vertex to be in point 1, 1. That's what this a is doing here, because I do have to fix the value of a in the correct way so that the total area under my function is equal to 1. So we're going to start by factoring the a out of the integral and expanding this part here. And we're canceling here 1 minus 1. And we're getting this. Well, there are other ways that I could have thought about this, right? Come to think of it, it would have been easier to think about the factored form of the quadratic function that has zeros at 0 and 2. But anyway, here we are. Now I've done the integral. The a is still hanging out there before everything else. 2x has been integrated to x squared, and x squared has been integrated to x cubed over 3. Now I'm going to have to use the fundamental theorem of calculus on both of these terms to integrate from 0 to 2. When I plug in the 0, it's just going to be 0, so the 2 is the only important one here. And I know that I want the result of this calculation to be equal to 1, right? So 4 is 12 over 3. 12 minus 8 is 4. Which means that the value of a needs to be 3/4. I'm also going to switch my function here for its factored form because it's going to simplify all of the calculations. And now we are going to start calculating all of the measures of central tendency and dispersion. But before you get too excited with all of the integration that you're going to have to do, always keep in mind that sometimes you don't have to do an integral. Sometimes you just look at it and the answer presents itself. So remember how in the previous example we didn't have to calculate an integral because we wanted the area of a triangle, for example, and things like that. So in this example, the mode is pretty obvious. The mode is the value with the highest density, which is 1. The median is also obvious because a quadratic function is symmetric around the axis of symmetry. So if the whole green area is 1, it's half on the left and half on the right, which makes the median equal to 1. And the mean is also going to be 1. Symmetric distributions do this. Everybody is in the middle. Remember in the discrete example that we actually calculated here, and unsurprisingly, it turned out that the expected value was the one in the middle because I had made a symmetric distribution. Also, if you think about the balancing thing that I was talking about before, this is symmetric. So if I put my finger in the middle, it is going to be balanced. So maybe the measures of dispersion here will actually require us to do integrals. Let's start with the IQR. Let's do the Q1 first. So the integral of the density from 0 to Q1 is supposed to be 25% of the probability. I'm going to multiply both sides of the equation by 4. And I've also factored out that 3 over there before I do the integration now. Once again, the integral is done. The fundamental theorem of calculus will only really have to apply to the point Q1 that we are looking for, because when we apply this function to 0, the result is 0. Multiply that 3 over there. But unfortunately, this one wouldn't be able to be a paper 1 question, right? So I've put that into my calculator, and it did give me 3 different answers for a polynomial of degree 3, but the other 2 were not good because one of them was negative and the other one was bigger than 1. I definitely want my Q1 to be to the left of the median. So now by symmetry again, if this is 0.65, then 2 minus Q3, this is going to be the same 0.65, and one minus the other is the IQR. Now I'm also going to calculate the variance for this example. I'm using the formula that we talked about before, and I'm going to distribute this f of x inside the parentheses. Notice that the 1 squared has disappeared because it's 1, but technically it's here, right? That's the mean squared. Now we can separate this into 2 integrals. And I know it seems weird to keep that 1 squared in there, but I wanted to show you what would happen to the mean squared even if it wasn't 1. So now I'm going to factor it out of the integral. And what's left here is an integral whose answer I already know. That's the integration in all of the domain of the function from 0 to 2 of just the function. So that's that green area over there, which is 1. So that minus mean squared that was already doing something kind of strange before. In practice, you don't even have to keep it inside of the integral. You can just integrate the x squared and then subtract the mean squared outside of everything. Okay, so now I have to substitute the f of x for the function that I have in the example. I've kept the 3/4 outside of the integral. Now I'm going to distribute here. And finally, we're going to integrate. So when I apply the fundamental theorem of calculus now, the second part of it, which is when I plug in the x equals 0, is just going to be 0, so I don't need to do that part. I am just going to plug in x equals 2 here. Okay, so there's a bunch of 2's over there. 2 and 2 to the power of 4 is 2 to the power of 5, but then divided by 2 to the power of 2, that's a 2 to the power of 3, which is 8. And here this is 32. So subtracting the fractions now, I'm going to get 40 minus 32, which is 8 over 5. I can cancel out this 4 here. I have a 2, so this is 6 over 5. 6 over 5 minus 1 is 1 over 5. So that's the variance, and the standard deviation is going to be the square root of that. So now we have all of the measures of central tendency and dispersion for this example. Let's go ahead and work on the next example. So next I wanted to show you an example that was not symmetric, so I took one of my favorite functions, which is x minus x cubed. When I sketch it in just this domain from 0 to 1, it doesn't really show why it's one of my favorite functions. But if you sketch it a little bit farther, you can kind of see, right? It is an odd function. It has 3 zeros, which are kind of easy to find. And as usual, I am putting that value of a there because I need to adjust it so that the area is equal to 1. So I went through all of the same steps here. I integrated the function from 0 to 1, used the fundamental theorem of calculus, and in order for the total area to be equal to 1, I'm finding that a needs to be 4. Now I'm going to start by looking at the mode. And now this is not symmetric. In the previous example, I didn't have to calculate anything for the mode because the vertex of the parabola was quite clearly the mode. But now I'm looking for a local maximum here. And the local maximum of a function is the point where the derivative is 0. And I'm ignoring the 4 here because it's not going to interfere when I put the derivative equal to 0. But I do want to comment that this is a point where a lot of students get confused, okay? So continuous random variables was a thing that was about integration, and all of a sudden I'm taking a derivative here. And then if you're not very familiar with how to do derivatives and integrals, you start to do them backwards, like increasing the exponent when you're supposed to decrease it, or vice versa. But listen, those difficulties are not really about random variables. They are about how familiar and how comfortable are you with calculus. And you really shouldn't be trying to memorize each one of these things. You should be trying to know all of the concepts. So on the other hand, you have the concepts from random variables, such as the mode is the turning point. And on the other hand, you have the concept from calculus, which is a turning point is when a derivative is equal to 0. So those two things you should know. And then when you need them, you put them together and say, oh, so the mode is when the derivative is equal to 0. You should not memorize the mode is when the derivative is equal to 0 out of context like this, as if it was a third thing to know, because it's not a third thing. We're talking about two things. The mode is the turning point, and the turning point is where the derivative is equal to 0. So anyway, this is an easy calculation to finalize. We end up with the mode being root 3 over 3. And now for the mean, we are again going to do the weighted average. So it's the values times their weights, which is the probability density, which you might think would turn into a more complicated calculation as the exponents of the x keep increasing. 3 and 1 is 4, and now integrate, now it's 5. But remember that all of that is going to disappear once I apply the fundamental theorem of calculus, because the 0 is not going to do anything, and the 1 doesn't care what the exponent is. So just 4/3 minus 4/5 is 8 over 15. The median might turn out to be a little bit more complicated because now the x is not going to be substituted by 1. It's going to be substituted by m and turn into an equation equal to half. So that is the kind of calculation that we might not be able to finish by hand. But we are definitely going to take the initial steps. There are a couple of numbers to simplify here. And now we are going to apply the fundamental theorem of calculus and set this equal to a half. Now I'm just going to organize this a little bit more, and it's looking now like it is going to be annoying, but it looks like it's something that I am going to be able to do by hand. So now I'm excited to see the end of this exercise. Because this is a polynomial of degree 4, but it doesn't have any odd terms, so I can treat m squared as another variable and use the quadratic formula here. Now I'm just going to simplify the numbers. This is the square root of 8, which is 2 root 2. Can simplify the fraction by 2 here. Now I want to think a little bit about which one of these two values for m squared I'm going to want, the plus or the minus. Because if one of them was turning out to be negative, then it would be an easy choice because m squared can't be negative. But that's not the case because 2 minus root 2 is still a positive number. Now, the thing is that the median needs to be a number between 0 and 1, because that's the whole domain of the density function. It's not going to be outside of the domain. And 2 plus root 2 over 2 is bigger than 1. So if we take an m squared that is bigger than 1, of course, the m is also going to be bigger than 1. So that's not what we want. I want the minus. So the median is the square root of that, right? M equals the square root of this fraction. I am very happy that I was able to do this one by hand without needing the help of the calculator. But now I am going to move on to measures of dispersion. I'm going to try to calculate the variance. I'm going to use the easy version of the formula here, okay? We've already talked about this, so I don't have to talk about it again. I'm just going to integrate x squared times the density and then subtract the mean squared. I already have the mean. And again, because this one is just a calculation, there is no equation to be solved. And the fundamental theorem of calculus is going from 0 to 1, which are very convenient numbers. This is just turning out to be a slightly ugly number, but nothing that I can handle. Here, I've even left my calculations on the board to prove to you that I did not use the calculator for this. I'm not going to finish the IQR calculation. I'm going to leave this as an exercise to you, but I've just begun it here to show you that it's totally going to be doable. It's going to be the same kind of thing as we did with the median, because this one is also turning into a polynomial of degree 4 that doesn't have any of the odd terms. So for the last example, I wanted to do something a little bit more complicated since I'm using the calculator now and I'm not going to have to work as much. So there are a couple of things that are going to be different from the previous example. First of all, I am using two different functions in my piecewise function besides the part that is equal to 0. So as you can see here, these are the two functions. One is a log and the other one is 1 over x cubed. There are also two constants now whose value I'm going to have to figure out. One of them is the a, just like in the other examples, that I'm going to have to choose a value of a to make the area equal to 1 for the whole function. But now there's also a value of b here, because I don't want my function to be very strange. So it should switch from one to the other at the point of intersection. The function should start at this log, reach the point of intersection, and then start going down again according to the 1 over x cubed. So the point B is going to have to be found, which is the point of intersection there. And before that, the function was just equal to 0 on the left. But the other thing that is also different now from the other examples is that on the right side of the function, I don't have that part where it goes back to just being flat and horizontal equal to 0. Instead, that function, which is 1 over x cubed, has a horizontal asymptote. Right, so the first thing that we're going to do is to find the point of intersection. We are going to do that as usual in the graph screen. We're going to go into this menu, choose the intersect, and the first curve is the blue one, the second curve is the green one. I'm going to put my guess anywhere because I know that there's only one intersection anyway. And there you go. That's the point of intersection, is kind of like 1.1. I wrote down a couple more significant figures there, but inside of the calculator, I do want to store even more. I want to use even more precision than that. And for that, I'm going to show you one of my favorite calculator tricks. After you've just finished doing anything in the graph screen, like we've just done, we found a value of x, which was 1.1. So at this point, if you quit the screen and you use the answer function, that right now has that last value of x that has just been found. So I am going to use that and use the store button down here to put that inside of a variable. I have the whole alphabet here that I can choose from in the green little buttons, but of course I am going to choose the letter B because that's what I'm calling this value in the problem. And from now on, the variable B just means what I want it to mean, and I'm never going to have to type this number 1.103 again. It's instead working with all of the precision that the calculator was able to find for it. And the next step is going to be to find the value of A. That needs to be chosen so that the total area under the curve is 1. So the first step is going to be to calculate the area under the curve. In order to do that, I'm going into the math menu and find the integration. But I'm going to need two integrals here, one for the log and one for the 1 over x cubed. So the log is going to be integrated between 0 and b, because that's the domain in which that is my density function. I also don't have to type the function again here because I've already typed it in the y equals screen. So instead, I can go into this menu here and choose the y1 because I remember that the log was in the y1, and that's what it's going to be using, and the integration needs to be dx as well. So that first part of the function is having an integral of 0.46. That is not the whole area under the curve, that's just the left side here. I still have to calculate the other side. And I'm going to calculate the other side in exactly the same way. The integral from b, now I would like to put it to infinity, right? Because there's a horizontal asymptote. There is no point where it stops being the function 1 over x cubed. But I can't put infinity here. That's not a number. So the idea is to put a very large number. And if you want to follow kind of similar to what we do in normal CDF problems, you would put 10 to the 99 here. But I don't want to do that. That is too big and it may slow down my calculations. So instead what I'm going to do is I'm going to try different values and see what happens, starting with 100. Okay? So the second function, I'm going to use the alpha menu as well, because that one has already been typed in the Y2, so I don't want to keep typing the same things over and over again. That's also an integration dx, and the value is kind of like 0.41. Now let's see what would change if instead of 100, I was doing 1,000. Well, that's a little bit bigger, but not very much. Let's put one more 0. Yeah, that's enough. I'm going to be treating infinity as 10,000 for the purposes of this exercise. But the total area under the curve is not just this number. It's this number plus the integral of the log function that I calculated before. It's this one here. So we are with a total of 0.87. That is not enough. We wanted that to be 1. So we are going to compensate for that with the variable a. A is going to have to be 1 over this number. That's a slightly bigger than 1 value, which is exactly what I need because I wasn't getting enough area. So what I want is to stretch it so it becomes more area. And just like I did with b, I am also going to store the value of a, this time obviously in the letter a, so that I can keep using this letter throughout my calculations without having to type anything again. Okay, so now we are going to start finding the measures of central tendency and dispersion. I'm going to start with the one that looks easiest, which is the mode. The value with the biggest density is clearly just b, right? The point where the two functions are meeting. Next, I'm going to do the mean. The expected value, remember, was an integral. So we have to do an integral, but it's not of just the density function. It's the integral of x times f of x. So let's type that here. X times f of x is stored in the y functions. I'm going to have to do two integrals. One for x times y1 and another one for x times y2 in their respective domains. So this one only goes from 0 to b. And then I'm going to add that to another integral, which goes from b to 10,000, the number that I decided is going to stand in for infinity. That integral is also of x times f of x, but in this part of the domain, f of x is the function that I typed in y2, so that I am getting this expected value here, but I can't forget that I didn't take the parameter a into account yet, okay? A wasn't typed into the y1 and y2 functions. So I still have to multiply this value by a to account for the fact that it should have been there. So that is the value of the expected value of my distribution. I'm going to store that one into a variable as well because I'm going to need it to calculate the variance. So I'm going to call this one m for mean. And the calculation for the variance is extremely similar. The only difference is that now I need the x's to be squared here. And of course, I need to be subtracting that m squared in the end. Let's see the results. You see, it takes a couple of seconds to calculate. That would be even longer in the actual calculator. The computer runs a little bit faster. but it's nothing that's going to prevent you from using it. Except I have just realized that I made a mistake here. I was trying to do everything in one line, including the subtraction of m squared, and I forgot about the a again. Because when we do the calculation for the integrals of the x squared times the functions, this also needs to be multiplied by a. That needs to happen before we subtract the m squared, because the m squared had already been calculated taking the a into account. So the variance is that number, and the standard deviation is just going to be the square root of the variance, which is like 2.9. The thing that's missing now is to calculate the median. And the median is interesting for these kinds of piecewise functions that have more than one part, because you don't know in principle if the median is before b or after b. So if the median is before b, then you only need to calculate with the first function. But if the median happens to be after b, then you need to calculate the first function all the way to b, and then the second function until m, and that's the area that's supposed to be equal to 0.5. We don't know which one of these things is the case until we calculate it. So first, let's try calculating just the left side, just the first function. Here I'm trying to prevent the same mistake from happening again. I'm already including a in the calculation line. And it turns out that the first function is enough to get to 0.5. It passes, it goes to 0.52. And what I want to do now is to solve this equation. I want to find the value of m that is going to make this integral exactly equal to 0.5. If I go all the way to b, like I just did, it goes 0.52. So it's going to have to be a little bit before b. So how am I going to solve this equation? The same way that I usually solve equations in my calculator, which is by graphing the left side and the right side of the equation separately and finding the point of intersection. The right side is quite easy, which is just 0.5, but the left side of the equation, I am going to have to type all of that. It's not really all that much typing because I'm using the same kinds of tricks that I've been using the whole time, where the y1 is a variable that I already typed before, so is the a. But even though it's not a lot of typing, it is a kind of a weird thing because this integral is dx, but I also want x to be m, which is the variable of my equation whose value I'm trying to find. So what I want to do is to put the x here, and then it looks so very weird. It looks like the calculator is going to confuse one x for the other x because they are not the same. However, that's just the way it is. She's not going to get confused. This is how you do it. So let's graph it. You see how it takes a while for her to graph as well, okay? This can get annoying if you're doing it in your calculator and it's taking a while, but still, in many situations, it's worth it. Now I want the intersection point between the pink and the red. So I'm going to use the same menu again, but now the first curve is not blue, it is red. The second curve is pink. It's whatever guess. It's giving me 1.069 for the median. And now I'm going to do the exact same thing to find the IQR. All I need to do is to put the 0.25 and the 0.75 also as functions here. She doesn't even have to graph again the function that takes her a lot of time because it's already there. Now I just need to find these 2 points of intersection. I was about to make a mistake there. Q1 is correct the way that I'm doing, but Q3 should not be in the intersection with that pink curve because the pink curve is only the integral of the log function, and that should only be used until b. We know that the integral of that log function until b is only about 0.53, so that's not going to be enough to reach the 0.75 that we need for Q3. Because the median was smaller than b, then we can be sure that q1 is also going to be smaller because it has to be before the median, but q3 is going to pass. So actually, the way that we need to calculate q3, we need to take into account this whole 0.53 here, and then add that to an integral from b to the point that we are looking for. I am doing that by first storing the 0.53 value with a lot of precision into the variable c here, and then graphing, as you can see in the last line here, it's c plus the integral from b to x. The problem is, though, that I'm going to have to change my window, because if I'm integrating from b to x, then it doesn't really make a lot of sense for x to be less than b. So I am changing my window to start at b. And the intersection between this new curve, which is the brown one, and the orange line, which is 0.75, that's what's giving me the value of Q3. And so finally, I am getting the value of the IQR for this example.